Hi guys, let us revise physics AS level structured questions from paper 2. This paper was written in May-June 2020 session, and let's get started. Alright. Use an expression for work done in terms of force to show that the SI base units of energy are kg meter squared per second squared. Okay, so work done is our energy. We can say we know the equation for work done is force times distance. We can break this down further. Force is mass times acceleration, then we multiply by distance. Let's bring in the SI units. The SI base units for mass are kgs, for acceleration are meters per second squared, and for x, which is the distance or displacement, they are meters. If we bring this all together, we get kg meter squared per second squared. So we have shown what we have been asked to show. Next one, the energy stored in an electrical component is given by that. Use this equation in the information in A to determine the SI base units of C. Alright, let's start by making C the subject of the formula. We can do this by multiplying both sides by C over E and this side by C over E. Alright, so if we do that, these ones will cancel out, these ones will cancel out. So we remain with C equal to Q squared over 2E. Now our C is in base. We have made the subject of the formula is C. For Q, let's determine the base units for Q, which is the charge. We can say Q is equal to current multiplied by time. So we know that current, the base units for current are amps, and multiplied by time, that's seconds. If we come to this, we have Q squared is A multiplied by S squared divided by 2 does not have any units. Then E, we have calculated the base units for E at the top. These were kg meter squared per second squared. So kg meter squared second squared. And if we go further, we have A squared S to the power of 2. I'll just bring the denominator to the top, to the numerator. So we also have S to the power of 2. Because we have inverted, the negative sign will go away. Then M to the power of minus 2 and kg to the power of minus 1. So M is minus 2, kg to the power of minus 1. If we unify everything, we will have A squared S to the power of 4, M to the power of minus 2, kg to the power of minus 1. Those are the base units for our C. All right. Measurements of a constant current in a wire are taken using an analog ammeter. For these measurements, describe one possible cause of a random error. Random errors are introduced by the user because of their, let's say, incompetence or inability to use the instrument properly. So with analog meters, one of the perfect candidates are parallax errors, which means, let me just say parallax reading from a wrong angle. You need to read your analog instrument from directly on top of the dial. If you read at an angle to the dial, there will be a challenge there. We also have analog meters which have, let me say, the accuracy of the instrument or the sensitivity of the instrument is not so well. So it may point, let's say this is 0, 5, 10, 15. And if our dial is pointing, let's say at that point, you may need to estimate, and that can introduce an error. So you may need to estimate when the dial is pointing in between values. That's an introduction of a random error. Systematic error, these are errors which are due to the poor calibration of our instruments. So let's just go straight for poor calibration of instrument. All right, so those are the causes of the errors that are mentioned. State Newton's second law of motion. We used to sing this one in our IGs. We would say in Newton's second law of motion says force is directly proportional to acceleration. However, there is a slight change nowadays. In AS level and A level, we present this as resultant force on an object is proportional to momentum. So that is our equation that we use now. So let me just correct the change in momentum. All right, we can show this by saying F is equal to MA, and we know that MA is delta V divided by T. So this is momentum, and divided by T, we now have P over T. Let's just put a delta there. So these are just different statements to say the same thing, but at AS level, this is more appropriate. This is what is expected from AS level student. All right. A delivery company suggests using a remote-controlled aircraft to drop a parcel into the garden of a customer. When the aircraft is vertically above and everything there, all right, the parcel takes that time after its release to reach point Q on the horizontal ground. On Fig 2.1, draw an arrow from point X to show the direction of the acceleration of the parcel when it is at that point. Okay, I picked this, which means our 5.4 meters per second will be constant throughout the flight of the flight of the object. The weight of the object is not balanced, so this is going to be the resultant force. The weight will be the resultant force, and the direction of the weight is going to be consistent throughout the journey. So when we are at X, the acceleration will point in the direction of the resultant force, which is our mg. So our arrow is an arrow that is pointing vertically downwards. Determine the height h of the parcel above the ground when it is released. All right. let's just put together the information that we have been given about this question. H is unknown. Acceleration is equal to g, which is equal to 9.81 meters per second squared. Then we also know that the initial velocity u is equal to 0 meters per second. The time of flight is the same for horizontal and vertical motion, so it is 0.81, okay, not meters but seconds. All right, so this is the data that we have when it comes to vertical motion. So this is the data that we have, and the most appropriate equation to use here would be h is equal to ut plus 1 over 2 gt squared. Sure, you are familiar with this equation. Let's substitute the values. This one is going to resolve to 0 because the initial velocity is 0. And if we put 1 over 2 times 9.81 times 0.81 squared, if we punch those values in our calculators, we should get 3.2 meters. So we have 3.2 meters there. Well, there's no need for me to include the m there because it's already given. All right, so let me just say something very important here. The presentation of our answer, I am using two significant figures because the least number of significant figures in my raw data is 2. So 0.81, there are two significant figures there, and 5.4, there are two significant figures. So it makes sense that I use two significant figures. Calculate the horizontal distance d between points P and Q. All right. One thing which is very important to notice here is, I've already mentioned that the horizontal velocity is going to remain constant throughout the flight of this object. And the time of flight for horizontal motion is equal to the time of flight in the vertical motion. So distance would be equal to our good old speed times time. And if we substitute the appropriate values, our speed would be 5.4 and our time would be 0.81. So in this one, we are going to get 4.4 meters. So we can come down here with the appropriate working, 4.4 meters. Well, that looks good to me. Let's move on. Another parcel is accidentally released from rest by a different aircraft when it is hovering at a great height above the ground. All right, let's see. On Fig 2.2, draw arrows to show the directions of the forces acting on the parcel as it falls vertically downwards. Label each arrow with the name of the force. Obviously, I expect everyone to know that this is the weight. We have weight, which is always pointing towards the center of the earth. And we also have this force, which is a resistance. You can give it as drag. All right, so these are the forces which are acting in their corresponding directions. Our air resistance should be vertically upwards because this object is falling vertically downwards. If it was falling at an angle, it would be a different ball game altogether. All right. I think that is sorted. By considering the forces acting on the parcel, state and explain the variation, if any, of the acceleration of the parcel as it moves downwards before it reaches constant or terminal speed. Let's consider the forces acting on the parcel to explain any changes of the acceleration before we reach constant. So it's before we reach constant speed. So as this object falls down, the weight of the object is going to remain constant. Yeah, I think that should be put down. Weight remains constant. However, the air resistance is going to increase. I just want you to imagine, suppose you have you have traveled in these cars which have sunny roofs. When the car is going slowly and you pop your head above the roof, the air resistance or the air hitting your head will be significantly less than if you pop your head whilst the car is traveling at great speeds. The difference in the magnitudes or in the amount of air hitting you is due to the speed. So when you are going at a faster speed, you will experience more drag than when you are going at a lower speed. So drag increases as the object falls. This drag is going to increase until it reaches a certain constant value, but we want to talk about the situation before we reach that value. So if weight remains constant and drag increases, it means the resultant force, which is the difference between, let me just call this D and this W, W minus D is going to decrease. Therefore, if our resultant force is decreasing, our acceleration will also decrease. So we can finally say resultant decreases and acceleration decreases as well. So those are notable events which happen before we reach terminal velocity. When we reach terminal velocity, acceleration would be 0, which means it has decreased to 9.81 until it got to 0. All right. Describe the energy convergence that occurs when the parcel is falling through the air at constant or terminal speed. So when we are at constant speed, one temptation is to believe that we are converting our gravitational potential energy into kinetic energy. Well, that is not correct because the kinetic energy is constant, and let me show you that. I know I'm not answering the question exactly, but I think it is important for us to address this. 1 over 2 mv squared. So at constant or terminal speed, m, of course, it will remain constant. The mass does not change, and the constant speed, well, it remains constant. So kinetic energy is not increasing. So where is this gravitational potential energy going? We are converting from GPE, gravitational potential energy, to thermal energy. This thermal energy, we can refer to it as internal energy of the rock. Why did I say the rock? Of the parcel. Okay, I think you may already know that when asteroids are falling into our atmosphere, they normally start to burn. This is similar to what will be happening to our parcel. The gravitational potential energy is now all being transferred into thermal energy, and if this parcel falls for long enough, it is eventually going to increase the temperature very notably. We are going to see a big increase in temperature. Otherwise, for very small heights, the increase in temperature is so insignificant that we rarely notice it. All right, to question number 3. State 2 conditions for an object to be in equilibrium. Well, for an object to be in equilibrium, the forces in the linear direction should be 0. That is, linear acceleration should be equal to 0. Then rotational acceleration should also be equal to 0. So to put this very easily, we can say in any linear direction should be 0, and also the resultant torque, that is now for rotation, should be 0. If these conditions are both satisfied, then our object will be in equilibrium. All right. A sphere of weight 2.4 newtons is suspended by a wire from a fixed point P. A horizontal string is used to hold the sphere in equilibrium with an angle that. All right. The tension T in the wire. Okay, let's calculate the tension in the wire. We know that for this object to be in equilibrium, let me pick a different color there. For this object to be in equilibrium, the horizontal should balance and the vertical forces should also balance. Now, going to the vertical forces, we can see that the weight should be balanced by the vertical component of T, and the vertical component of T is T sine 53 degrees. Now if we substitute the values, we will have 2.4 is equal to T sine 53, and our T is going to be 2.4 divided by sine 53. If we punch in the numbers properly, we are going to get our T being equal to 3 newtons. All right, let's go to the next. The force F exerted by the string on the sphere. All right, we have this force which is going in the horizontal direction. This force is being balanced by the horizontal component of T. So we can safely say F is equal to T cos 53. T cos 53 is the horizontal component of T, which is balancing our F there. And if we substitute the values, we have 3 cos 53, and let's see, we get 1.8. So here we have 3.0, and at the bottom we have 1.8 newtons. That looks easy enough. The wire has a cross section of diameter 0.5 millimeters. Determine the stress in the wire. Okay, let's see the wire properly. Okay, all right. So stress is equal to force over cross-sectional area. Now we know the force which is acting in the wire is equal to the tension. The cross-sectional area, we have to calculate it using the data that we have just been given there. We know the cross-sectional shape of the wire is circular. So we can go on to say, let me just do it there, area is equal to pi d squared over 4. And this is equal to pi times 0.5 times 10 to the power minus 3. Make sure you substitute, you convert your diameter to SI units, which are meters. Everything divided by 4. Alright, so I'm not going to resolve this one because I want to preserve some accuracy there. I'm going to come down here and say 3 divided by pi times 0.5 times 10 to the power minus 3, or divided by 4. If we punch that into our calculator, we are supposed to get 1.5 times 10 to the power 7. That's quite a lot of stress in that wire there. All right. The string is disconnected from the sphere in B. The sphere then swings and all those things happen. Let's see the questions. Show that the vertical distance h between A and B is 15 centimeters. All right. So what we are going to do is, let's extend this. Okay, that is not very nice. All right. And here. So this is 75 centimeters, and we don't know this yet, but the distance h is this one. We can see that 75 centimeters minus x is going to give us h. Now we can easily get we can get x easily by using the trig equations. Now we know that sine 53 is equal to opposite, which is our x, divided by hypotenuse, which is 75 centimeters. Therefore, x is equal to 75 sine 53. If we do our calculations, we'll get some value. I'm not going to calculate that because I want to preserve the accuracy. I don't want to round off before we get to the final value. But now h is equal to 75 minus 75 sine 53. And this is going to give us h being equal to 15 centimeters. So we have shown that the distance between the vertical distance is 15 centimeters. Very easy there. Calculate the change in gravitational potential energy of the sphere as it moves from A to B. Okay, GPE is equal to mg delta h. All right, that's right. Let's see if we have the mass. Okay, so mg is equal to 2.4 because weight is equal to mg. So we have 2.4 multiplied by delta H, which is 15 centimeters, but we are going to say times 10 to the power minus 2. We want to use meters, therefore our change in GPE, I think it's also appropriate to put the delta there. Change in gravitational potential energy would be equal to 0.36 joules. Perfect. Use your answer in C item 3 to determine the speed of the sphere at B. Show your working. All right. Let's do this. We know that 1 over 2 mv squared, the kinetic energy which is going to be gained by our ball or the pendulum is equal to the change in GPE. So if we say 1 over 2 mv squared is equal to mg delta H, we can cancel the m's and we can have v squared being equal to 2g delta H, and then v will be equal to square root of 2g delta H. If we substitute the right numbers, 2 times 9.81 times 15 times 10 to the power minus 2. Punch that into your calculator. You should get speed as 1.7 meters per second. Okay, I'm so into writing the units today. All right, that looks very clear. All right, number 4. By reference to the direction of propagation of energy, state what is meant by the longitudinal wave. Guys, with this question, I just want to make you aware of two things which are happening here. Energy is being propagated in a particular direction, and we have particles which are oscillating in a particular direction. When we are answering this question, we must mention the relationship between the direction of propagation of energy and the direction of oscillation of particles. Here we are talking about the particles which are in the medium where the wave is traveling, or through which the wave is traveling. So we can say the particles vibrate parallel to the direction of propagation of the wave. All right, so this is how we can define the longitudinal wave. Examples of longitudinal waves are like sound waves, and we know that if the wave is going in this direction, we have refractions and compressions, meaning our particles are extending outwards and coming back to the equilibrium position. All right, state the principle of superposition. With the principle of superposition, you have to mention that when two or more waves meet, there should be two or more So I'll just underline the key points. When those meet, their resultant displacement is the algebraic sum of the individual displacements of the waves. So that's quite a lot. All right, so that is our principle of superposition. All right. This is Young's double slit experiment. The data is shown in the diagram, and okay, the fringes are the fringe separation is shown there. There's nothing really tricky about this one. They try to really give it to us, so we can say A is equal to 3.7 times 10 to the power minus 4 meters. A is our slit separation. Then D is equal to 2.3 meters, and D is the distance of the screen from the slits. What else? Our X is equal to 4.3. X is the thickness of the fringe, or the separation between adjacent fringes. So 4.3 times 10 to the power minus 3. Given this information, we can substitute it in the equation, which says lambda is equal to ax over d. And if we substitute the values, we can say lambda is equal to 3.7 times 10 to the power minus 4 times 4.3 times 10 to the power minus 3, or divided by 2.3, and we will get our wavelength. Punch that in the calculator, you will get 6.7 times 10 to the power minus 7. So that is the wavelength. You see, they want us to present our answer in nanometers, so we must change it to, all right, so this is going to be 670. All right, this is supposed to be 9. All right, so this is supposed to be 9, and if we change it to nanometers, we have 690 times 10 to the power minus 9. I don't need to do that. 690 times 10 to the power minus 90 with minus 90, and I'm now confused. All right, like that. All right, so that is our wavelength. It really pays to be looking at this value, or at the unit which you are supposed to use in your answer presentation. The intensity of the light passing through each slit was initially the same. The intensity of the light through one of the slits is now reduced. Compare the appearances of the fringes before and after the change of intensity. One thing is for sure, the separation of the fringes is not affected by the intensity of our lights. Of course, they may look blurry because one of the slits is no longer very intense, but the separation will be the same. All right. Then The bright fringes. Bright fringes are formed when two waves meet and their path difference is equal to n multiplied by lambda. So we can say path n lambda. Now if one of the waves is now less intense and the other wave is still intense, this less intense is going to contribute less to lighting up the bright fringe. So eventually the bright fringe will be less bright. And let's look at the dark fringes. At the dark fringes, we have, let's say this is the first wave. The intensity is still the same. Remember, the intensity corresponds to the amplitude. Then this is the other wave. The intensity is now reduced. This second wave was supposed to cancel this wave completely. That is a complete destruction of the waves during destructive interference. But now that its amplitude is no longer same magnitude of the first wave, it is going to fail to cancel it out completely. So the dark fringes are not going to be as dark as they were supposed to be. The dark fringes will be a little brighter. Let me say less bright, less dark. All right, so the dark fringes are going to be less dark. Okay, let's go to question number 5. A metal wire is used to connect a power supply to a lamp. The wire has a total resistance of that value. Resistivity is given and the length of the wire is also given. Alright, show that the wire has a cross-sectional area of that value. We are going to use the equation R is equal to rho L over area. R is the resistance of the wire, rho is the resistivity, L is the length of the wire, and A is the area. Now let's make area the subject of the formula. A is equal to rho L divided by R. We substitute the given data. Let's check the SI units. All the data is in SI units, so we can continue. 2.6 times 10 to the power minus 8 times the length, which is 59, divided by the resistance, which is 3.4. If we punch those values in our calculators, we will get 4.5 times 10 to the power minus 7. Alright, that one is sorted. The potential difference across the total length of the wire is 1.8 volts. Calculate the current flowing in the wire. Alright, from V is equal to IR. I would be equal to V divided by R. If we substitute the data that we are given, let's check our 1.8 for voltage and resistance. It will be 3.4. All right, so if you punch into your calculator, you will get 0.53 amps. That is the current which is flowing in our wire. Awesome. The number density of free electrons in the wire is this value. Normally refer to this as N. Calculate the average drift speed of the free electrons in the wire. All right, so we are going to say current is equal to cross-sectional area multiplied by number density multiplied by the drift speed of the electrons multiplied by the charge of each charge carrier. In this case, it is the electrons. If we make V the subject of the formula, we have V is equal to I divided by A N Q. And if we substitute the appropriate data, we have 0.53 divided by the cross-sectional area. Let's see what was that value. 4.5 times 10 to the power minus 7. Our N is given there as 6.1 times 10 to the power 28. And our Q, this is the elementary charge, which is 1.6 times 10 to the power minus 19 coulomb. All right. Just a few presses in our calculator will give us the drift speed as 1.2 times 10 to the power minus 4 meters per second. All right, I think that makes sense. A different wire carries a current. This wire has a part that is thinner than the rest of the wire, as shown in Fig 5.1. I think, though we have not been asked, you already know that a thinner wire has more resistance there. Let's see what they want us to say. State and explain qualitatively how the average drift speed of the free electrons in the thinner part compares with the rest of the wire. Alright, when they say qualitatively, you do not really need to bring in numbers or calculations. You just have to describe what happens without any calculations or percentages or fractions involved. So qualitatively, let's do this. We know that the equation for drift velocity is this. The current on this thin part is going to remain the same. The elementary charge is going to remain the same. The number density of the material is going to remain the same, but the area, the cross-sectional area, is going to be less. So if area is less, it means the value of V is going to be bigger. So the drift speed will increase. N and Q and I remain constant. Cross-sectional area is now smaller. So V is going to increase. Alright, I think that makes sense. State and explain whether the power dissipated in the thinner part is the same, less, or more than the power dissipated in an equal length of the rest of the wire. Alright. So we can see that on the thinner part of the wire, the resistance is going to increase. And if we use the equation, power is equal to I squared R. If the resistance increases, then the power is going to increase. Remember, our current is remaining constant. So the area of the thinner part is less, so from R equal to rho L over A, R increases, and from P is equal to I squared R, power dissipation increases. So those are the events, or those are the reasons why our power is going to increase. We have three resistors with resistance of 180, 90, and 30 ohm. Sketch the diagram showing how two of these resistors may be connected together to give a combined resistance of 60 ohm between them. Alright, so with this one, you may need to do a little trial and error, but eventually, maybe before the trial and error, it's obvious that we are not going to have a series connection here, because when resistors are in series, the total resistance is simply the sum of the resistances. So here we cannot see any combination whose sum will lead to 60 ohm. Therefore, we should try parallel connections. And after a couple of trial and errors, the parallel connection that works is the 180 and 90. 180 ohm and 90 ohm. Let's just confirm that very quickly. 1 over total resistance is equal to 1 over 180 plus 1 over 90. 1 over R T would be equal to 1 over 60. And if we invert, we will get our RT being equal to 60 ohm. There is a quicker way, but I think it's good to just go with the fundamental way, the basic way. All right. A potential divider circuit is now produced by connecting the three resistors to a battery of electromotive force 12 volts, a negligible internal resistance, and that. All right. So we want to see a combination of resistors which is going to give us 8 volts and 4 volts. Well, if one set gives us 8 volts, the other set should give us 4 volts. So either we have 4 volts here, or we have 8 volts there, or we have 8 volts there and 4 volts there. So let's see the combinations which can split our voltage in the given proportions. The proportions of the voltage are 1:2. So I think this is a follow-up on this question, because we already know that this combination gives a resistance of 60 And if we couple that with a 30 volts, let's see, we will achieve the 8-4 resistance, a potential difference. Sorry. So let's put our 30 here. Let's put 180 and 90. Let's use this combination to see 30 divided by, okay, let's see, 30 divided by 30 plus 60 multiplied by 12, 30 divided by 90 times 12. Alright, so we are going to have a 4 volts here, and we will have the 8 volts here. We know when the resistance is bigger, the potential difference across the resistor will be bigger as well. And since our potential difference was in 1:2, we can also expect a 30:60, which is basically 1:2 ratio on the resistor side as well. All right. Okay, so the number 5 is done. Two horizontal metal plates are separated by a distance of 2 centimeters in a vacuum as shown in Fig 6.1. All right, determine the magnitude of the electric field strength between the plates. All right, electric field strength, E is equal to V divided by D, where V is the potential difference between the plates and D is the separation of the plates. So if the potential difference is going to be 180 minus 120, and the plate separation is 2 centimeters, that's 0.02 meters. Plug in our values in a calculator. We are going to get our electric field strength as 1.5 times 10 to the power 4 newtons per coulomb. Then state the direction of the electric field. It always flows from the positive to negative. So in our diagram, it will be from top to the bottom. This might have been easier if we had been asked to just label between the plates there, but it is what it is. So an uncharged atom of uranium-238 has a change made to its number of orbital electrons. This causes the atom to change into a new particle ion X that has an overall charge of +2e, where E is the elementary charge. Determine the number of protons, neutrons and electrons in the particle ion. So if we change the orbital electrons, it means the protons remain as they used to be. So the protons will be 92. The neutrons we say 238 minus 92, and that is going to give us 146. Originally we had 92 electrons and 92 protons. That's why our our atom was not charged. Positive and negative were balancing out. When we removed 2 electrons to cause a deficit of 2 negatives, it means our electrons became 19. So that is the number of the particles required. The particle X is in the electric field in A at a point midway between the plates. Determine the magnitude of the electric force acting on X. Alright, I think we have E equal to F over Q from the definition of electric field strength. Therefore, our F is equal to E multiplied by Q. Our E is the value that we just calculated. I think it was 1.5 times 10 to the power 4. Then the charge is 2 multiplied by the elementary charge we removed. We have an excess of 2 protons, so 1.6 times 10 to the power minus 19. Punching into our calculators, we get 4.8 times 10 to the power minus 15 as the force which is going to act on particle X. This field is uniform. I think we can agree this field is uniform. So it does not really matter whether our particle is in the midway or closer to the X or closer to one of the plates. It's a uniform field. The nucleus of uranium-238 decays in stages by emitting alpha particles. Alpha particles, they are basically helium nuclei. So we have 2. And beta minus particles. Okay, so when we decay by beta minus, how are our beta minus, they are electrons. So beta minus, it look like electrons. All right. By the way, we have beta minus and beta plus, so just have to be careful around those ones. Calculate the total number of alpha particles and the total number of beta minus particles that are emitted during the decay of uranium-238 to that. Alright, there are 2 things which we can notice here. We are changing from 238 to 230. Now we know that when we have an alpha decay, the proton number of the nucleus is going to decrease by 2 and the nucleon number is going to decrease by 4. We can see a decrease of the nucleon number, a decrease of 8 in the nucleon number. So this points towards 2 helium or 2 alpha particles to be specific. And if we think of the beta minus decay, in beta minus decay, the proton number increases by 1 and the nucleon number remains the same. So if proton, okay, at the top, since these were 2, we saw a decrease of 4. There are 4, a decrease of proton number of 4, and if we compensate that decrease by an increase of 2, we are going to have an overall change in proton number of 2. So let's see if that matches what we have there. So here, when we took away 4 alpha particles, we were taken to 88. and when we took away 2 beta minus particles, we were taken to 90. When we took 2 alpha particles from the top, we were taken straight to 230. So these are our numbers. So we have 2 alpha particles and 2 beta particles. Okay guys, I hope this is helpful and have a very good time. Bye bye.